Hi, my name is Sanat Kanda, and today I'll be presenting my final project for Microprocessor Applications 2, which is a real-time weather Internet of Things app. This project integrates hardware and software and real-time operating systems to create an interactive weather information system. Over the next few minutes, I'll walk you through how this works, the components involved, and the lessons I learned along the way. So, an overview of the project. The goal of this project was to design a system that provides real-time weather updates in a user-friendly format. The system uses an ST7789 TFT display to show weather data such as temperature, chance of precipitation, wind speed, direction, and humidity. The users can navigate through pages of weather data for four main cities: Tampa, Florida; New York City, New York; Daly City, California; and Chicago, Illinois. The To ensure seamless multitasking and synchronization, the project relies on the TOS, which is a real-time operating system specifically designed for the Tiva C microcontroller, which we created and then implemented in Lab 4. This allowed me to focus on efficient task management while creating responsive user interfaces. The hardware components that I used the microcontroller, the Tiva C board, which is used to process the input-output signals, and it also manages the display and runs the gator toss to handle multitasking. The screen is the ST7789 TFT display that came on our microprocessors applications to lab kit. The input output buttons are also used, and the BeagleBone Black communicates with a server through a WebSocket, retrieves the data, and sends it to the Tiva over UART4. These components work together to deliver weather updates more efficiently in real time. So now for an overview of the Gator Toss. The Gator Toss is a real-time operating system which was central to this project. I designed it in Lab 4 and implemented it in Lab 4, and it is designed for the Tiva microcontroller and provides the following features: the thread management, which enables multitasking by dynamically handling multiple threads using a round-robin scheduling system. It has semaphore support, which helps manage the shared resources and prevents conflicts between threads. And it has inter-process communications, or IPC, which are mechanisms such as FIFOs, which allow efficient data transfer between the threads. This system ensures that the tasks like data fetching, processing, and display updates run smoothly and in sync. So some of the elements I used, so these are the threads that I used for this project. The background threads that I used, I have the idle thread, which serves as a fallback when no other threads are running. It keeps the CPU occupied, so that way, in a case where no other thread is running, the CPU isn't just floating or stalled. The display update refreshes the data on the screen using the data retrieved from the BeagleBone Black, and the periodic threads are the get data thread, which periodically requests and receives weather data from the server via UART. It processes the data and updates the FIFO buffers for display threads. The aperiodic threads that I have are the button handling thread, which responds to the button press and allows the users to navigate between the pages. The GPIOE handler is part of the button thread, where it's just an interrupt handler for the button press and debouncing the buttons, make sure that the buttons are handled properly, and it was the most efficient way that I could handle the button presses. So the Gator Toss, the semaphores that I used for the Gator Toss were SPI semaphore, which manages the access to the SPI bus for communicating with the TFT display. The UART semaphore, which controls access to the UART interface, and the semaphore for displaying pages. The done drawing semaphore, which signals that the display update thread is finished drawing. The button semaphore, which communicates between the button interrupt handler and the read button thread, make sure that they're working in sync. And the update thread, which updates the coordinates to the display based on the button presses or the initial system state. So the NOAA, or the National Oceanic and Atmospheric Administration, offers a free API which returns weather data based on latitude and longitudinal coordinates. By sending requests to this API, the system ensures that the data displayed is accurate and up to date, and that's it. The way the overall code works is my laptop acts as the server for the entire project, but my laptop requests data from the NOAA API. The API returns data in the form of JSON packets, and the laptop receives and processes it to the BeagleBone. I'll explain more about that in the next slide. So server-client communication, the server being my laptop and the client being the BeagleBone. The way it works is the server contains a list of latitude and longitudinal coordinates of the four cities that I mentioned earlier. The server sends requests to the NOAA's API to fetch weather data for these cities. Then it sends the data to the BeagleBone in a structured format that I specify. Then once it's received by the BeagleBone, the BeagleBone extracts the relevant data and transmits it to the Tiva via UART port. It periodically requests new data every 2 seconds and ensures that the system remains current. And this client server setup ensures seamless and reliable data flow. So communication between the BeagleBone Black and the Tiva. The BeagleBone Black and the Tiva use a structured communication protocol. I have it so that first there's a handshake protocol where the Tiva sends a null character to signal readiness and receives data. The data transmission then engages, and the BeagleBone sends weather data in segments, with each segment terminated by a null character. The data reception and parsing part is the Tiva receives the data character by character and stores it in buffers, and then writes that to the FIFO to be used by the display thread. And I synchronize this by using a UART semaphore, which manages access to the UART interface and ensures data transmission and reception occur without any errors or conflicts. This protocol is robust and ensures that the Tiva accurately displays the data it receives. And it makes sure that the Tiva only works when there's new data. But the only issue is sometimes when there's a lag in the overall NOAA API requesting server, it might lag the app in general. But I traded that for having a more reliable system just because I was having issues when I would just send the UART data to the Tiva. It would misalign the received data with the buffers so that it would replace, for example, the city name with the temperature or something, and it would be out of sync. This way, everything is in sync, and even though it might lag sometimes, it's at least reliable and works very somewhat efficiently. So lessons I learned, this project has been a tremendous learning experience, and I learned a lot in this course in general. I learned about implementing I2Z sensors for real-time data acquisition with the accelerometer, the gyroscope, the light sensor, which I put in my project in case like I would go further and make it a smartwatch or something. So I can use that data to change the different orientation of the app and things like that. I learned how to design and utilize a real-time operating system for multitasking. And I established network communication between a server and a client. And I also learned how to do request and handling for API data for real-world applications. So in conclusion, this project was a perfect blend of hardware and software and networking. This class in general showed me how to use real-time systems and how they can deliver practical user-friendly solutions. And yeah, now I'll move on to the demo.
So this right here is a visual of how my final project looks like. So it's on page 2 right now, but I'm going to change to page 1. And so on page 1, it shows the city name, the temperature, the percent of rain, the percent chance of rain. On page 2, it shows the city name, the wind speed, the humidity, and on page 3, There's sensor data in case I wanted to make this a smart watch or something like that. See, it shows the accelerometer data, the gyroscope data. So you can change it. See, it updates every 1 second. It's a periodic thread. And the light sensor, if I cover it, it decreases. If I bring my lamp closer, it increases. And yeah, so the way I have it working right now, as you can see, the server gets the information from the NOAA's API. It collects the JSON list and then it sends it over to the BeagleBone, which then, as you can see, it processes the JSON list and sends it via UART as a string to the Tiva board, which then updates the screen to the, it updates the screen with the current weather data. And in the bottom corner, I have the page. So I have 3 pages, right? And I have it updating periodically every 1 second. Just because that's how I'm receiving the lists, I'm going through an array that has a lat-long coordinates for each city. And as each city, I collect the data for 1 second, and I have it change every 1 second or so. Yeah. And you can see the UART print statements as it's receiving. And the display itself is a background thread. I have it just updating just the portion where the city displays to save the refresh rate and have it work relatively quickly. Obviously, this switch is a little bit slow, but that's because it's activating on a UART interrupt handler. And I have the whole thing working based on whenever it receives data, the interrupt handler will trigger and it'll update the buttons and the display, which is why it's a little bit slow. But other than that, yeah, this is just for future use in case you want to make a smartwatch, like an Apple Watch or something. You have it wake to cover, you can like have it rotate or something. I tried making that mechanism, it didn't work that well. But yeah, other than that, once again, this is page 2. It cycles through Tampa, Florida, New York, Daly City, and Chicago every second. And all this data is from the NOAA's database that I'm using. I'm using my laptop as a WebSocket to get the data. But yeah, other than that, that is my final project.